Part 12. The behavior of measuring rods and clocks in motion. I place a meter rod in the x prime axis of k prime in such a manner that one end, the beginning of the rod, coincides with the point x prime equals 0, while the other end, the end of the rod, coincides with the point x prime equals 1. What is the length of the meter rod relatively to the system K? In order to learn this, we need only ask where the beginning of the rod and the end of the rod lie with respect to K at a particular time t of the system K. By means of the first equation of the Lorentz transformation, the values of these 2 points at the time t equals 0 can be shown to be as follows. X for the beginning of the rod equals 0 multiplied with square root of 1 minus v squared over c squared. X for the end of the rod equals 1 multiplied with square root of 1 minus v squared over c squared. The distance between the points being square root of 1 minus v squared over c squared. But the meter rod is moving with the velocity v relative to k. It therefore follows that the length of a rigid meter rod moving in the direction of its length with a velocity v is square root of 1 minus v squared over c squared of a meter. The rigid rod is thus shorter when in motion than when at rest, and the more quickly it is moving, the shorter is the rod. For the velocity v equals c, we should have square root of 1 minus v squared over c squared equals 0. And for still greater velocities, the square root becomes imaginary. From this, we conclude that in the theory of relativity, the velocity c plays the part of a limiting velocity, which can neither be reached nor exceeded by any real body. Of course, this feature of the velocity c as a limiting velocity also clearly follows from the equations of the Lorentz transformation, for these become meaningless if we choose values of v greater than c. If, on the contrary, we had considered a meter rod at rest in the x-axis with respect to k, then we should have found that the length of the rod, as judged from k prime, would have been square root of 1 minus v squared over c squared. This is quite in accordance with the principle of relativity, which forms the basis of our considerations. A priori, it is quite clear that we must be able to learn something about the physical behavior of measuring rods and clocks from the equations of transformation. For the magnitudes x, y, z, t are nothing more nor less than the results of measurements obtainable by means of measuring rods and clocks. If we had based our considerations on the Galilei transformation, we should not have obtained a contraction of the rod as a consequence of its motion. Let us now consider a second clock, which is permanently situated at the origin x prime equals 0 of k prime. T prime equals 0 and t primes equals 1 are two successive ticks of this clock. The first and fourth equations of the Lorentz transformation give for these two ticks t equals 0 and t equals 1 over square root of 1 minus v squared over c squared. As judged from k, the clock is moving with the velocity v. As judged from this reference body, the time which elapses between two strokes of the clock is not 1 second, but 1 divided by square root of 1 minus v squared over c squared seconds, which is somewhat larger time. As a consequence of its motion, the clock goes more slowly than when at rest. Here also the velocity c plays the part of an unattainable limiting velocity.